In the final week of January 2026, astronomers announced something extraordinary. 3I Atlas has entered a configuration so rare that nothing comparable will occur again for decades. The setup emerging in mid-March represents one of those cosmic coincidences that turns routine observation into a historic opportunity. Here's what's happening. In approximately 6 weeks, the comet will pass through an angular sector measuring less than 10 degrees wide in the sky. Within that narrow slice, several key objects align closely from our perspective: the Sun, Mercury, Venus, Earth, Mars, Jupiter, and the interstellar visitor itself. Think of it as 7 celestial bodies appearing nearly threaded through the eye of a cosmic needle, all visible from Earth within a field narrower than your fist held at arm's length against the night sky. The alignment itself is remarkable enough, but there's a second layer that elevates it to genuinely exceptional. During this same period, 3I Atlas will sweep past Jupiter at a minimum separation of just 0.36 astronomical units. That translates to roughly 54 million kilometers, which in planetary terms is an unusually close encounter. Statistical analysis suggests that for any random interstellar object entering the solar system, the probability of passing this near to Jupiter is well below 2%. We're watching an event that combines geometric rarity with dynamical improbability. Now consider what this means from an observational standpoint. Multiple planets in near alignment create subtle gravitational influences that affect trajectories. Jupiter, with its immense mass, will exert measurable perturbations on the comet's path. Those perturbations offer a natural experiment, allowing astronomers to refine measurements of the comet's mass, velocity, and response to gravitational stress. Every interaction provides data that helps constrain models of what this object is made of and how it behaves under forces it hasn't experienced since leaving its home system billions of years ago. The timing could not be better for observers. By late January, every major observatory with capability in the relevant wavelengths had already updated target lists to prioritize 3I Atlas during the March window. Infrared telescopes will track thermal signatures as the comet navigates different solar intensities. Spectroscopes will monitor chemical emissions for any changes triggered by the shifting gravitational environment. Radar installations will attempt to map surface features with unprecedented resolution as geometry temporarily favors Earth-based instruments. If you're following this story and want to stay updated as we move through February into the alignment itself, now's a good time to subscribe. The data coming in over the next 2 months will likely reshape several assumptions about how interstellar objects behave when threading through planetary systems. But here's the part that makes this more than just a scheduling coincidence for telescopes. Planetary alignments of this type occur roughly once every few decades, depending on how tightly you define the angular constraints. An interstellar comet passing through the solar system at any given time is itself a rare event. We've confirmed only 3 such objects in all of human history. The intersection of these 2 rare phenomena happening simultaneously pushes the combined probability into territory that astronomers describe with phrases like once in a century or possibly unique in the observational record. What we're seeing unfold is not just an alignment, it's a convergence of trajectories that were set in motion long before Earth existed, now intersecting in a configuration that offers a brief window to study an object from another stellar system under conditions we may never see again. The comet didn't plan this encounter. Jupiter didn't steer into position to greet an interstellar visitor. These are simply the mathematical consequences of velocities and orbits determined millions or billions of years ago, now converging in our sky during a span of weeks in early 2026. As March approaches, the question shifts from whether this is remarkable to what we'll learn from it. The answer depends on what instruments capture during those critical days when geometry, gravity, and opportunity align. The photometric data released in late January revealed something that shouldn't be there. The dust tail of 3I Atlas now stretches beyond 250,000 kilometers, which alone would mark it as one of the more impressive comet displays in recent years. But length isn't the anomaly, direction is. Standard comet behavior follows a predictable pattern. Radiation pressure from the Sun pushes dust particles away from the nucleus, creating a tail that points almost directly away from our star. Minor deviations occur, typically a few degrees at most, caused by the comet's orbital motion sweeping particles into a slight curve. What observers measured in January defies that pattern entirely. Significant portions of the tail deviate by up to 140 degrees from the Sun nucleus vector. Instead of streaming away from the Sun, large sections of dust appear to be moving almost perpendicular to the expected direction. The explanation lies in something we don't normally see in comets: particle size. Typical cometary dust consists of grains smaller than 100 micrometers. Think particles finer than beach sand, easily pushed by solar radiation. Analysis of 3I Atlas shows a dust population dominated by particles larger than half a millimeter, approaching the size of small pebbles. At that scale, radiation pressure becomes less effective. Other forces take over: gravitational interactions with the nucleus, momentum from sublimating gases, even subtle effects from the comet's rotation. Here's where it gets interesting. The presence of millimeter-scale particles in such abundance suggests the nucleus is shedding material through a mechanism more violent than gentle sublimation. Something about the internal structure or composition is generating enough force to eject relatively large chunks. Those chunks then follow ballistic trajectories that depend more on their initial velocity and direction than on solar pressure. The result is a tail that looks less like a wind-blown streamer and more like debris scattered from multiple sources. Now, look at what this tells us about composition. Producing millimeter-sized particles in large quantities requires either a very cohesive surface that fractures into chunks rather than crumbling into dust, or a subsurface layer that occasionally releases bursts of material with enough energy to overcome surface gravity. Both scenarios point to a nucleus very different from what we see in solar system comets. Most of our local comets are described as dirty snowballs, with ice binding together fine dust. 3I Atlas appears to be something structurally distinct, possibly with less ice relative to refractory material, leading to a harder, more fragmented surface. The tail orientation also provides a clock of sorts. Particles of different sizes leave the nucleus at different times and respond to solar forces at different rates. By mapping the distribution of dust along the tail and measuring how orientation changes with distance from the nucleus, astronomers can reconstruct the ejection history over the past several weeks. Preliminary models suggest at least 3 distinct ejection events in December and early January, each producing a pulse of large particles that now form the curved, misaligned structures visible in images. What questions does this raise about where 3I Atlas came from? If you're tracking this story closely and wondering how a comet forms with this kind of dust profile, drop your thoughts in the comments. The working hypothesis involves formation conditions very different from the outer solar system environments that produced our comets, but we're still piecing together what those conditions might have been. The dust tail isn't just a visual spectacle, it's a diagnostic tool revealing internal processes. Every particle in that 250,000 kilometer streamer carries information about ejection velocity, surface temperature, nucleus rotation, and composition gradients. As observatories continue tracking through February, they're building maps of where specific particle sizes concentrate, how the tail morphology evolves, and whether new ejection events occur. One more detail worth noting: the sheer length of the tail combined with the particle size distribution allows observers to estimate mass loss rates. Early calculations suggest 3I Atlas is shedding approximately 10 to 20 kilos of material per second. For a nucleus estimated between about 0.4 and several kilometers in effective diameter, that's a substantial fraction of total mass being lost over the course of its solar system passage. If this rate continues, the object may look significantly different when it eventually departs than when it arrived. The dust tail of 3I Atlas is doing something most cometary tails don't. It's misbehaving. And in astronomy, anomalies are where we learn. On November 16, 2025, the VLT telescope pointed its spectroscope at 3I Atlas and captured something unprecedented. The nickel-to-iron ratio in the gaseous coma measured between 0.9 and 1.1. To understand why that number matters, consider that most solar system comets show nickel-to-iron ratios below 0.2 to 0.3. Even 2I Borisov, the previous interstellar comet, never exceeded 0.4. 3I Atlas was producing nearly equal amounts of nickel and iron vapor, a chemical signature unlike anything in the existing cometary catalog. But here's where the story becomes more complex. That extreme ratio didn't persist. As the comet moved outward from perihelion, which occurred on October 29 at about 136 astronomical units from the Sun, the nickel-to-iron ratio began dropping. By January 2026, it had fallen to approximately 0.35, still elevated compared to typical comets, but nowhere near the peak values measured in November. Something about the comet's thermal state was changing its chemical output. The pattern follows a mathematical relationship. Analysis shows that nickel to iron depends on heliocentric distance according to a power law with an exponent of 1.15 plus or minus 0.05. In simpler terms, as the comet moves farther from the Sun and surface temperatures drop, nickel emissions decline faster than iron emissions. This temperature dependence points to different volatility thresholds for nickel-bearing and iron-bearing compounds in the nucleus. At higher temperatures near perihelion, both metals sublimate readily. At lower temperatures farther out, nickel-bearing materials stop outgassing while iron compounds continue. Now consider what this tells us about the nucleus interior. Metals don't sublimate easily. Iron and nickel in comets typically exist either as fine dust grains or as components of more complex minerals. For these metals to appear in the gas phase requires temperatures high enough to vaporize solid material or break down metal-bearing molecules. The fact that 3I Atlas produces such high metal concentrations suggests either an unusually high abundance of volatile metal compounds in the ice or sufficient heating to directly sublimate metal grains. The gas production rates measured after perihelion provide additional context. Cyanogen was being produced at approximately 2.1 tons 1025 molecules per second. Diatomic carbon followed at 1.4 x 1025 molecules per second. Triatomic carbon, a less common species, reached 3.6 x 1024 molecules per second. These rates place 3I Atlas among the more active comets observed at similar distances, though not exceptionally so. What stands out is the ratio between different species and how those ratios compare to solar system comets. Spatial mapping of the emission reveals another layer of complexity. Jets of nickel, iron, cyanogen, and diatomic carbon all emerge within 20 degrees of the anti-solar direction. They're being pushed outward by the same active regions following similar trajectories as they escape the nucleus. But triatomic carbon behaves differently. Its emission jet deviates by more than 45 degrees from the Sun nucleus line. This geometric separation indicates that triatomic carbon originates from a distinct active region, one located on a different part of the nucleus surface. What does multiple active regions tell us? It suggests a heterogeneous nucleus with varying composition or thermal properties across its surface. Some areas might have more ice, others more refractory material. Some regions might face the Sun more directly, receiving more heat. The uneven distribution of active regions creates the complex outgassing pattern that produces multiple jets pointing in different directions. As the nucleus rotates, different regions move in and out of sunlight, creating temporal variations in gas production and changing the appearance of the coma. Here's a question worth considering. If 3I Atlas formed in a metal-rich environment around another star, what does that tell us about the protostellar disk chemistry there? If you've been following interstellar object discoveries and have thoughts on what kinds of stellar systems produce comets like this, the comment section is open. The formation environment matters because it constrains what planetary systems might look like beyond our immediate neighborhood. The metal chemistry of 3I Atlas isn't just unusual, it's diagnostic. Every emission line captured by spectroscopes represents a molecule that formed billions of years ago in a disk around another star. Those molecules got incorporated into a comet nucleus, survived the journey through interstellar space, and are now sublimating under the sun's heat. We're watching chemistry from another stellar system playing out in real time, and the ratios don't match what our own system produces. That mismatch is the signature of a different origin written in the language of atoms and wavelengths. The nucleus of 3I Atlas measures somewhere between roughly 0.4 and several kilometers in effective diameter. That range comes from combining radar returns with photometric modeling, both techniques aimed at estimating size for an object too small and distant to resolve directly. But size alone doesn't capture what makes this nucleus remarkable. The density does. Current estimates place the average density at approximately 0.4 to 0.6 g per cubic cm in some models. For context, water ice has a density of about 0.9 gram per cubic centimeter. Rock typically exceeds 2.5 gram per cubic centimeters. A nucleus with such low density, despite containing substantial rocky and metallic material, can only achieve that through extreme porosity. The nucleus isn't a solid block, it's more like a rubble pile, a loose aggregate of ice, dust, and rock held together by weak gravity and whatever cohesion the ice provides. Void space likely accounts for more than half the total volume. This porous structure has direct consequences for thermal behavior. Modeling shows that heat from the sun penetrates only 3 to 5 meters below the surface. Beyond that depth, material remains at the cold temperatures it maintained in interstellar space, potentially below 50 Kelvin. The shallow heating creates a stark gradient, a warm, active surface layer underlain by a frigid, inert interior. This configuration explains the uneven outgassing observed spectroscopically. Only the surface regions heated above critical sublimation temperatures contribute to gas production. Deeper material stays frozen, insulated by the porous upper layers that conduct heat poorly. Now connect this to the multiple active regions identified through jet mapping. A heterogeneous surface combined with shallow heat penetration means that composition variations, even a few meters deep, can determine whether a particular spot becomes active or remains dormant. If one region has slightly more ice or a thinner dust coating, it heats up faster and starts outgassing sooner. If another region has a thicker refractory layer, it acts as an insulator, preventing subsurface ice from warming. The result is patchy activity with discrete jets emerging from specific locations while surrounding areas remain quiet. The porosity also affects mechanical strength. A nucleus that's mostly empty space doesn't hold together strongly. Sublimating gas can build up pressure in subsurface pockets, eventually fracturing overlying material and releasing bursts of dust and gas. This mechanism could explain the millimeter-sized particles observed in the tail. Instead of gentle sublimation lifting fine dust, you get more energetic events that break off larger chunks. The low density means even modest pressure buildups can overcome the weak cohesion holding surface material together. Consider the implications for long-term stability. A porous, fragile nucleus subjected to heating and outgassing undergoes structural changes with each close approach to a star. Material sublimates away, voids collapse, and the surface reorganizes. Over billions of years wandering through the galaxy, encountering stellar systems, and experiencing repeated heating cycles, such an object would be significantly altered. The 3I Atlas we're observing now might look very different from the body that first formed in its home system. We're seeing an evolved object shaped by time and exposure. Thermal models can project forward. If the nucleus continues losing mass at current rates and maintains its porous structure, substantial fractions of the surface layers will be eroded by the time it exits the inner solar system. The object departing will have a different mass, different rotation, potentially altered by asymmetric outgassing, and an exposed surface that was formerly buried interior material. It's not the same comet leaving that arrived. Here's something worth thinking about. If low-density porous structures are common among interstellar comets, what does that tell us about survival during the ejection process from their home systems? If you found this analysis interesting and want to help surface more science content like this, consider leaving a like. It genuinely affects how these videos get distributed. The physical structure of 3I Atlas reflects a formation environment and evolutionary history we're still working to understand. Every measurement of density, porosity, and thermal properties provides constraints on models of how such objects form and how they respond to heating. The low density and shallow heat penetration create the observed chemical signatures, the uneven jets, and the unusual dust tail. Structure determines behavior. And in this case, the structure is telling us we're dealing with something assembled under very different conditions than the comets we know, a fragile, ancient rubble pile traveling between stars for billions of years, now briefly warming under a foreign sun. The interior stays cold, the surface fractures and sublimates, and we measure what emerges. That's the physical reality of 3I Atlas. Fragile, ancient, and temporary. The chemistry, structure, and behavior of 3I Atlas all point toward a formation environment fundamentally different from the outer solar system. The hypothesis emerging from multiple lines of evidence suggests this object originated in a metal-rich, water-poor region of a protoplanetary disk. Instead of forming beyond the snow line where water ice dominates, it might have assembled in a warmer zone where metals and refractory materials were more abundant, then got ejected before those materials could fully differentiate into a rocky body. The age estimate adds another dimension. Models place formation somewhere between 4 and 7 billion years ago. That predates the solar system itself, which formed roughly 4.6 billion years ago. 3I Atlas is potentially older than Earth, older than the Sun, a survivor from an earlier generation of star formation. It formed around a star that may no longer exist, in a galaxy that was younger and potentially had different average metallicity than the Milky Way today. The object carries information encoded in its composition about conditions that existed before our own planetary system began assembling. According to Avi Loeb, a prominent astronomer who has extensively studied interstellar objects, these visitors function as natural probes, delivering material from other stellar systems. Each one provides a direct window into the chemical evolution of planetary systems beyond our own. Unlike light from distant exoplanets, which travels through atmospheres and gets filtered before reaching our telescopes, interstellar objects bring actual samples of matter formed around other stars. We can analyze isotopic ratios, mineral structures, and chemical abundances directly. It's the closest thing to a physical sample return mission from another stellar system, except the sample delivers itself. But 3I Atlas remains only the third confirmed interstellar object. 1I Oumuamua passed through in 2017, notable for its elongated shape and lack of cometary activity. 2I Borisov followed in 2019, displaying cometary behavior more similar to solar system comets. 3I Atlas represents something different again. Extreme metal content, unusual dust properties, and dynamic behavior that sets it apart from both previous visitors and local comets. With a sample size of 3, we can't yet determine whether each interstellar object is unique or if patterns exist. That statistical problem is about to change. The Vera Rubin Observatory, currently in final commissioning phases, will begin systematic sky surveys with unprecedented sensitivity. Projections suggest it will detect 5 to 10 interstellar objects per year once fully operational. Within a decade, we could have catalogs containing dozens of interstellar visitors, enough to start identifying patterns, classifying types, and determining whether 3I Atlas represents a rare anomaly or a common category we simply hadn't sampled yet. This is where the story transitions from a single remarkable object to a broader question about galactic material flows. Stars don't hold on to all their planetary material. Gravitational interactions during system formation eject significant fractions of planetesimals into interstellar space. Models suggest the galaxy contains trillions of these wandering objects, outnumbering stars by many orders of magnitude. Most are small, dark, and cold, detectable only when they pass extremely close to the Sun, but occasionally we catch one during an active phase, outgassing and bright enough to study in detail. Each interstellar object carries a formation signature. The ratios of different elements, the presence or absence of certain minerals, the structural properties all reflect the conditions in the disk where it formed. By studying enough of these objects, astronomers can start mapping the diversity of planetary system chemistries across the galaxy. We can ask questions like, how common are metal-rich formation environments? Do certain types of stars produce certain types of interstellar objects? Has the average composition of ejected material changed over galactic history? 3I Atlas currently stands as the most chemically and dynamically complex interstellar object ever recorded. Its metal-rich composition, unusual dust behavior, multiple active regions, and low-density porous structure all mark it as exceptional within our limited sample. But exceptional compared to what? We have 3 data points. The Vera Rubin Observatory will multiply that by 10 or more within its first few years of operation. In the immediate term, observations will continue through the March planetary configuration, tracking how the comet responds to Jupiter's gravitational influence and evolving solar heating. By mid-year, 3I Atlas will have moved beyond effective observation range for most instruments, fading as it heads back toward interstellar space. The data collected over these months will be analyzed for years, feeding into models of cometary composition, interstellar object dynamics, and protoplanetary disk chemistry. But the broader significance extends beyond this single object. 3I Atlas has demonstrated that interstellar visitors can be radically different from anything in our local inventory. It has shown that material formed around other stars under different conditions can survive billions of years in interstellar space and arrive here still carrying clear chemical signatures of that origin. It has proved that we can extract detailed information about distant stellar systems not through telescopes pointed at faint dots of light, but through direct analysis of matter that traveled across light years to reach us. Each interstellar object is a messenger from a place we cannot visit, carrying a story written in atoms and molecules. 3I Atlas told a story of metal and fire, a formation in an environment richer in refractory materials than our own system's birthplace. Future visitors will tell different stories, and gradually we'll learn whether the galaxy's planetary systems share common patterns or display vast diversity. The answer will reshape our understanding of planet formation, chemical evolution, and our place within the broader population of stellar systems. 3I Atlas was a beginning. The next decade will determine what it was the beginning of.